So now I want to go through another very common type of proof, which is a proof by contradiction. Okay. This is very common because oftentimes it's hard to prove things directly. There might not be a clear line of sight from your hypothesis to your conclusion. So what you do is you kind of do an indirect proof, proof by contradiction. So I think the best example of this is kind of the canonical proof that square root of 2 is irrational. Okay. This is probably by far the most famous proof. In fact, there's an entire book written of different ways you can prove this. But this is like the canonical proof by contradiction. So I think just going through it carefully is the best way to see exactly how this type of proof works. Okay. So the idea is that you say, okay, we want to prove square root of 2 is irrational. So there's two choices. Either square root of 2 is irrational or it's rational, right? Those are mutually exclusive. It's got to be one or the other. So let's go ahead and assume it's the other one. Let's just say assume square root of 2 is rational. Okay, so now we're going to show that this leads to a contradiction. This leads to some nonsense statement. And then what we see from that is that, okay, if square root of 2 is rational, that implies something we know is not true. And then we kind of trace it back up the chain and say, well, this was true, this was true. So the only thing that wasn't true is our original statement. So therefore, it can't be rational, which forces it to be irrational. Okay, so this works for these dichotomous statements where you have to have one or the other, right? If maybe there's three options, then you could show that two of them don't work or something like that. So, and another note on why we even want to do this, well, showing the square root of 2 is irrational, it's hard to formulate an irrational number, right? That doesn't give us a lot to work with. There's not like a nice form that we can use there. But square root of 2 is rational. Rational does have a form, right? So square root of 2 is equal to a divided by b, where a and b are integers, right? So this gives us something to work with here. Not a lot on first glance, but it's something. Now, this proof hinges on this next statement here, which is that assume a, b is equal to 1, okay, i.e. a and b have no common factors. Okay. So this is saying the greatest common factor of a and b is equal to 1. Why are we allowed to assume this? This is a key point. Well, if a and b do have common factors, then we could just cancel those factors out and then call the new things like c and d or something, and then we're just right back where we started. So we're fine assuming that they have common factors. Otherwise, again, we just cancel them out, and then whatever the new integers are, that's our new a and b. Okay, so this is a key part here. So we're assuming that they have no common factors. So this gives us something to work with now, because now we can show, well, they must have common factors. And then we're kind of in this loop of illogicalness, if that's a word. So square root of 2 is equal to a over b. Okay, well, this implies 2 is equal to a squared over b squared, right? Just using some algebra, which implies that 2b squared is equal to a squared. Okay. Now this implies that a squared is even. Now, does this imply that a is even? Because this is key. We want to get back to a and b, and it does. Okay, this implies that a is even. Now, I don't think this is something we should just take for granted. This is a bit of a leap, right? It's not something that's immediately obvious. You could think of it about it, though, right? We can think it's easy to show. I'm going to do this in red just so we know this is kind of an aside here. it's easy to show it in the other direction, which is that if a is even, then a squared is even, right? If a is equal to, say, 2n, then 2n squared is equal to 4n squared, which is equal to 2 times 2n squared. So this is even, right? So we've shown this direction, but what about the other direction? So this is a case where we might want to look at the contrapositive, which is that, okay, does a is odd imply that a squared is odd? Okay. These are logically equivalent, right? This is the contrapositive. Because odd means not even, right? So a is not even would imply that a squared is not even. This gives us something a little easier to work with, because if we start trying like a squared equals 2n, then you have a is equal to the square root of 2n, and there's not a lot to work with there, right? We don't really know anything about n. The square root of 2 doesn't really help us at all. So this is going to be a lot easier to prove, because now we just say, okay, a is equal to 2n plus 1. So 2n plus 1 squared equals 4n squared plus 4n plus 1 equals 2 times 2n squared plus 2n plus 1 is odd. Okay, so this is true, which means that this original statement is true. Okay, so we flip it around to the contrapositive. That makes it much easier to prove. A lot of the proofs you go through won't actually show this, but I think it's good to see this because it's not an easy proof, and it gives us another example of when we should use the contrapositive. So in other words, if a is not even, then a squared is not even, which implies that if a squared is even, then a is even. So anyway, why does this matter? Well, all right, so a is even, great. So that means that a is equal to some number 2 times, did we already use k? I don't think we did, right? It's good to not use reuse letters. So a is equal to some number 2k, where k is in z. Okay. So what we have here is that 2b squared is now equal to a squared, which is equal to 2k squared, which is equal to 4k squared. Okay. Now this is going to imply that b squared is equal to 2k squared. And that's going to imply that b squared is even, which implies then that b is even. Okay. So here we just sub in a, and then we do some algebra. And then we say, okay, well, then I divided both sides by 2, right? So we have b squared equals 2k squared. So now b squared is 2 times some number, which makes it even. And we just showed that b squared being even implies b is even. So what do we get from this? Well, this tells us, so a and b are both even, meaning they have a common factor of 2. Okay. And that's a problem, right? Because now this is contradicted. This one right here, right? Where it says, assume that they don't have any common factors. And we already went through why it's okay to assume that. What you could do now, if you don't even want to assume that, you could say, okay, we'll cancel their common factor. Now these are our new numbers, and then you go through the proof again, and you'll just keep getting in this loop where you show that they're always going to both be even, implying that you could just keep canceling a 2 forever and ever and ever, which doesn't make any sense, right? So that we lead to this contradiction here. We're contradicting this statement, which was a fine statement. So therefore, if we trace this back and look for, okay, what went wrong? Well, it's the original statement that's wrong, right? So therefore, there can't be any numbers square root of a and b such that the square root of 2 is equal to those numbers. Otherwise, we get caught in this infinite loop of canceling factors. So therefore, the square root of 2 must be irrational. Okay. So what we would say is that this is a contradiction. So square root of 2 is irrational. Okay. So this can be tricky. You really need to make sure everything along the way is correct. So that only the initial statement is the only possible thing that could be wrong. Okay. And here's a good example of why. So here's an example of a bad proof. Okay. So let's say that A is equal to B. Okay, where A and B are if you want to say that they're not zero, sometimes you could write this as like they're real numbers minus the set of 0. Okay, so this means that they could be any real number except 0, or you could just write non-zero. But anyway, so this means that A squared is equal to A times B, right? Just multiply A on both sides, no problem there. Then we're going to subtract B squared from both sides. Okay. And then we're going to factor. So everything we've done so far is fine. So this is A plus B, A minus B is equal to B times A minus B. Okay. Now we can cancel A minus B on both sides. So this means A plus B is equal to B. And then we subtract B from both sides. And we get that, or I'm sorry, no, we don't subtract B from both sides. We say, okay, A plus B, A is equal to B. So this implies that B plus B equals B, which implies, of course, that 2B is equal to B, which implies that 2 is equal to 1. Okay. So that's a bad proof. Sometimes you'd see people like, oh, I can show 2 plus 2 is equal to 5. And it's somewhat similar to this, right? So maybe you notice exactly where this went wrong, maybe not. It can be kind of sneaky, right? You see these kind of go viral on social media sometimes where, you show 2 is equal to 1. Well, the main problem here is when we cancel the A minus B, of course, because A is equal to B, so A minus B is 0. So here we divided by 0. Okay, and we can't do that. This is why we can't do that. It leads to contradictions. So the point here is we have to make sure every step along the way is sound. When we're reading a proof or writing a proof or whatever, right? This part was fine. Canceling the B here is fine because B is not equal to 0. So it's fine to cancel the B here. The only thing that is not fine is dividing by 0. So there's a famous story about this from Bertrand Russell, which is pretty funny, but basically he says that, if you start with the idea that 1 is equal to 0, I can prove that I am the Pope. And what he means by it is if you start with an incorrect assumption or use an incorrect assumption, you can prove anything, right? You see this sometimes with infinite series. Like if you take a divergent series, you can make it equal to pretty much anything, but it's not equal to anything because it diverges. So there's an interesting Numberphile video on that, if you've ever looked at that channel, where you can look at the, I think it's the sequence of like 1 plus 1 minus 1 plus 1 minus 1 plus 1, you can show that it's equal to 1/2. But it's really not equal to anything because it's divergent. But anyway, so he says if you take 1 equals 0, you can prove, I can prove that I am the Pope. And then a student raises his hand and asks him to do it. And he says, 1 is equal to 0. So add 1 to both sides. That means 2 is equal to 1. The set containing just me and the Pope has 2 members, but 2 is equal to 1. So it only has 1 member. So therefore, I am equal to the Pope, right? So again, the idea is if you start with something illogical or you use something illogical like division by 0, you can show anything. So we have to make sure that the logic is following in every step. That's the key thing here.